Welcome to the Cosmic Savannah with Dr. Nathan
and Dr. Jacinta Delhaze.
Each episode, we'll be giving you a behind-the-scenes look at the world-class astronomy and astrophysics happening under African skies.
Let us introduce you to the people involved, the technology we use, the exciting work we do, and the fascinating discoveries we make.
Sit back and relax as we take you on a safari through the skies.
Hi everyone, welcome to today's episode of the Cosmic Savannah. With you today is myself, Jacinta.
And me, Tiamiso.
And Dan is somewhere in Africa. I think he's in Ethiopia.
I mean, the last time when we were recording, he was somewhere in Suits in Pretoria, and now he is right in the heart of Africa in Ethiopia.
Traveling a lot, but don't worry, he'll be back soon. So it's just the two of us today, but we have an exciting episode for you. Today we are talking to Dr. Nathan Deg from Queen's University about polar ring galaxies.
I mean, that is just already so interesting. Polar ring galaxies. Mm-hmm. And it already sounds like these are just not normal galaxies. These are not galaxies we've spoken about before.
No.
So Jacinta, tell us a bit about them.
So these are what you imagine a galaxy to look like. It's like a flat, like a dinner plate if you look at it on the side, and it has these beautiful spiral arms if you look at it kind of face on, and it contains stars, it contains big clouds of gas and dust all swirling around the center together. But polar ring galaxies also have, as the name suggests, a ring in a polar direction. So that means that there's this huge ring of maybe it's stars or maybe it's gas going kind of perpendicular to the plane of the spiral of the flat dinner plate. If you imagine holding a dinner plate flat and then, I don't know, standing a carrot on top, that would be in the perpendicular direction. And so you've got a ring going all the way around the galaxy and, well, we call around the poles, and so we call it a polar ring galaxy.
I mean, that's quite interesting. And you were studying H1 galaxies, right? Or galaxies within the H1 region.
Yes, I'm studying the H1 in galaxies. So that means the hydrogen gas, which is in a neutral state. So that means it's kind of cold gas. It hasn't been ionized by the high energy particles that are out there in space. It's been kind of protected and it's cold, and it can eventually form stars. So it's kind of like the fuel for the galaxy, or the food for the galaxy, if you like. And there's a lot of that inside a galaxy. Yeah.
And so we will find a lot of that also in polar ring galaxies, right?
Yes, you can. So sometimes the ring itself is made almost entirely of hydrogen, of this, what we call H1 is the short name that we call it. And yeah, that's what we're going to be talking about today, a galaxy with a polar ring made entirely of hydrogen gas.
I mean, that's fascinating and quite amazing. So what kind of tools or instruments was used to get data for these galaxies?
Yeah, so this is, you can study these things with radio telescopes, because we've talked about this before on the podcast, but it's my favorite subject because it's one of my research fields. So I'm so glad you've asked me all of these questions.
She's always excited.
Yeah, so it is the hydrogen gas actually emits a signal. It kind of glows in radio wavelengths. So we can see it with a radio telescope, such as our very own beloved Meerkat telescope in the Karoo in South Africa. But there's also another telescope that can see it. It's ASCAP, which is the Australian SKA Pathfinder, and that is in the Murchison region of Western Australia, where I'm actually from.
That is quite interesting. So they've used data coming from Australia, but actually, you know, the person that we're talking to is in Queen's University, which is actually in Canada.
In Canada, yeah.
So just reminding us how actually the science that we do always brings us together, even though we are in different parts of the world. So I think that is quite interesting.
That's right, yeah. So the telescope itself is in Australia, and a lot of the researchers who use it are based in Australia, but we work as part of these big teams, and each team kind of has a name, and the teams can be of astronomers anywhere in the world. So I'm part of this team, for example, that uses the ASCAP telescope, and our team name is called Wallaby. So Wallaby is the name of our team, and also the name of we call it a survey that we're performing. So you take your telescope and you choose a patch of sky, or maybe it's the entire sky, as it is in our case, and you observe it in a certain way for a certain reason. And the name Wallaby, it stands for, I had to look this up because I can never remember it, but it's Wide Field ASCAP L-band Legacy All-Sky Blind Survey.
Yeah.
Yeah.
That's a long acronym, but you know,
Yeah.
Wallaby sounds a lot more cool. So
Yeah.
the Wallaby Survey.
The Wallaby Survey. It's a name of an Australian animal, a little kangaroo sort of, but not quite.
Okay.
Yeah. So that's what a wallaby is, and we're going to hear all about that from Nathan. So I won't go into too much detail, but basically, it's looking at the entire southern hemisphere sky and trying to detect the faint signals of hydrogen gas. And with this Wallaby Survey, Nathan and his collaborators found not one but two polar galaxies.
So that's one of the latest discoveries from the Wallaby Survey, right?
Yeah, it is one of them. And so Nathan has published a paper with his colleagues and put out a big press release, and a beautiful image of these or at least one of them, these polar galaxies, was created.
And how was that created?
I'm so glad you asked.
I think that's what's capturing me right now, just the creation of that and how the scene or tried to visualize this ring around the galaxy.
Well, that's actually where South Africa comes in. And so we have a very cool visualization laboratory here at the University of Cape Town. And some of the technology that's part of that was used to create a virtual reality image of this data, which was actually used to help identify that this object was a polar ring galaxy. And we're actually going to split this episode into two parts. So today we're going to be hearing from Nathan Deg about the science and the paper research itself. And then in the next episode, we're going to hear from Dr. Lucia Marchetti and almost Dr. Alex Civitili, who are from the University of Cape Town, and they're going to give you and me, Tia, a tour of the visualization lab.
I mean, I can't wait. Okay, maybe I'm lying. I can wait.
Because we have just done it. And we're recording after that. But
also because literally the Viz Lab is right above my office. So
Oh, that's true. That's true. Cool. All right. So the final thing to say is that polar ring galaxies, still a mystery about how they're created, but it could be due to the collision of two galaxies. But I'll let Nathan explain all of that.
Yeah, so let's hear from Nathan about these polar ring galaxies.
With us now, we have Dr. Nathan Deg from Queen's University, all the way in Canada. Welcome, Nathan.
Thank you so much for having me. It's fantastic to, I'd say, be here, but, this is slightly cross-continental.
Yes, we are via Zoom, but you have been on the Cosmic Savannah in the studio before, haven't you?
Yes, I have. It was lovely. It's a wonderful studio, and anyone who gets a chance should absolutely go and visit it.
Our tiny weird studio behind the files. Yeah, so Nathan, you were actually in our first season of the Cosmic Savannah on episode 9, all about simulating galaxies. And I think that was in 2019. So we're like 4 years later now. And you are now in Canada. You used to be at the University of Cape Town and now you're in Canada.
Yes, I am. So I've got an interesting position now where my main job is not in simulation land anymore, but it is now in galaxy modeling and observation land instead. So switching over.
Galaxy observation and modeling. Is that what you said?
Yes. So
Okay.
I'd say it's more observing in the sense of, even though I still don't use telescopes directly, but my job now is kinematically modeling galaxies. And so when someone has observed the gas content of a galaxy, so the neutral hydrogen, using something like, well, in this case, it's Wallaby on the Australian Square Kilometre Array Pathfinder, but also you could do it with Meerkat. There's really no real difference in terms of modeling techniques. The idea is to go and figure out how fast the gas is moving at different spots and how much gas there is and what the geometry of the whole system is. And so that's what I work on now.
All right, so let's break,
for the most part.
Let's break that down a bit. Okay, so you're looking at gas in galaxies. So what kind of gas?
So we're looking at neutral hydrogen. So that's the most dominant form of the gas. So most of the gas is going to be neutral hydrogen in the disks of galaxies. And that's what galaxies are turning into stars, ultimately. Well, it goes from neutral hydrogen into molecular hydrogen, but we don't need to go into all the details of star formation.
Okay, so within galaxies, you have stars, you have gas, and you have like massive clouds of gas and dust, and the gas can be in different forms, and we need the gas in order to fuel star formation because it's the raw kind of food, or it's the fuel for galaxy to form new stars. And you're saying that most of the gas in a galaxy is in the form of neutral hydrogen gas.
Yeah, there's a lot of nice things about it. And one of the useful things for people who worry about what galaxies are made of, and particularly are worried about dark matter, you want to be able to trace out the galaxy as far as possible. And the hydrogen gas almost always goes out further than the stars for spiral galaxies. So I'm going to restrict a little bit to spiral galaxies because a lot of ellipticals don't have much gas.
Okay, so there's different types of shapes of galaxies in the universe. We've got ellipticals, which are like big kind of footballs or soccer balls or whatever sport you're into. And we've got spiral galaxies, like flat like dinner plates, but with like these nice, beautiful spiral arms. And the spiral galaxies have a lot of gas, and the elliptical galaxies we think generally don't have as much gas.
Yeah.
But then, like, where does a galaxy end, right? Like, how do you define the edge of a galaxy?
Yep, that's a good question. I was at a conference before talking about this whole definition, that was the focus of it, on both how do you define a galaxy and where does a galaxy end, and was talking about all sorts of complicated ideas of, well, galaxies have dark matter, so shouldn't we be defining the end of a galaxy by the dark matter? But we can't see dark matter, so that's a ridiculous idea. But the theorists were all like, but that's what it is in our simulations.
Okay, so you're saying that, like, when we look at a galaxy with like an optical telescope like the Hubble or the JWST, what we see as a galaxy is we're only seeing the stars, right? And we can see how far out from the center the stars exist, like in a nice disk. But then what we can't see with these optical kind of light that we can see with our eyes is the gas. But then if we use a different kind of telescope, we can see the gas, and it's extending way further out than the stars. Is that right?
Yes, absolutely. That's 100% correct. Now, the tricky bit is, of course, again, even when we talk about the edge of a galaxy, is the more sensitive your telescope, oftentimes the further out you can find stars, and sometimes the further out that you can find gas, but with neutral hydrogen, there is a limit to how long out that it can still be neutral hydrogen, sort of thing. So there is a bit harder of a limit, but we're still not there in... Even Meerkat, which is such a beautiful telescope, isn't seeing all the neutral hydrogen that you could possibly see, sort of thing. We want to go out even further.
What happens when you go out even further?
Well, the simulations get wonky. You see all this nebulous gas that might be falling in from sort of more a cosmic environment, cosmic filaments, and this sort of thing. And this is one of the early motivations of this square kilometer array, is that we want to know how gas gets onto galaxies. So one of the mysteries of galaxies is how are stars still forming? And so we know that we can turn gas into stars. And we can measure how fast gas gets turned into stars. And when we do that and calculate, well, if this has gone on this long, we should have used up all the gas in the galaxy really quickly. But as far back as we look in time, galaxies have gas and they are forming stars. So that means that we have to be getting gas in. It's the same way if you're driving. If you run out of gas in your car stops. But you can stop at a petrol station and fill up. So somehow galaxies are stopping at petrol stations and filling up on their gas content because they're just burning through it way too fast. So we have to figure this out. But the simulations say there is gas out there, but it's far fainter than we can see, and we're going to need the square kilometer array to see some of that accreting gas and where it's coming from.
Okay, so there's two ways we can study this very faint hydrogen gas so that we can tell what's going on at the edges of galaxies. One is with simulations, which we're going to talk about in a minute, and the other is with observations, with telescopes. So you've mentioned the SKA, you've mentioned ASCAP, you've mentioned Meerkat. What are these and why can these see gas?
So these are radio interferometers. So what they are is a whole bunch of radio dishes pointed up at the sky that are working together to collect the light from neutral hydrogen. So neutral hydrogen is, again, it is an atomic gas, but it emits light at a radio wavelength. It has a specific, what we say, a spectral line at 21 centimeters. So if we think about the light that we normally see is in the 500 nanometer range. So this is much, much longer, orders of magnitude. But radio dishes have the ability to see that light, and when you have interferometers, you use all the dishes together to collect the light. So the idea behind the square kilometer array was to have enough dishes that the entire size of the collecting area was an entire square kilometer. But then they were going to spread those dishes across, the continent of Africa for what we call the SKA mid. So they're building it now. Meerkat's going to be part of it. And again, the more dishes you have, the more sensitive that you can be, but it also is incredibly computationally intensive to make these observations and build these instruments. They are marvels of the modern world. And the SKA is probably the biggest scientific enterprise that we've ever attempted on Earth from a computing and technological standpoint.
Wow.
Or at least that's my opinion.
Yeah, me too. It gives me like goosebumps every time I think about it. Okay, so that's the SKA, but we can't just like go ahead and build this massive thing. We have to have build some test telescopes first. So the first one we've built is, one of the several that have been built is Meerkat, which is right here in South Africa. But then there's another one, isn't there, in Australia?
Yeah, ASCAP, which is the Australian Square Kilometre Array Pathfinder. And I think ASCAP and Meerkat, in many ways, are very complementary. So Meerkat is amazing. It has more sensitivity and better resolution. But what ASCAP has, it still has incredible sensitivity and incredible resolution compared to everything that's come before it. But it also has an insanely large field of view. A large field of view for a telescope would be a square degree, which is pretty large on the sky. ASCAP has a field of view that's 30 square degrees. So it's ridiculously large relative to other interferometers that have been built before.
Yeah, and just for comparison, it's about half a square degree across, right?
Yeah, so this thing, it's looking at so much of the sky, and it's got a unique combination of field of view, sensitivity, and resolution, and that makes it sort of a discovery machine. And then when you find interesting things there, then you can go ask Meerkat, or it was something in the north, you could ask VLA, but, the overlap there is very low. So there's the Very Large Array in North America. You have to be able to look at the same part of the sky, and that's not a huge overlap. So
yes, well, I know you're in the Northern Hemisphere, but we're going to ignore the Northern Hemisphere for now because it's far less interesting in the sky than the South.
As one should. But yeah, so with this, you can go and ask someone else to go, hey, we found something really interesting. Could we look at it with a higher resolution and with more sensitivity to get deeper observations? So I'm part of a survey called Wallaby, where Wallaby is going to look at the H1 content of galaxies for most of the southern sky. And so that gives us a unique ability to find interesting objects that maybe we hadn't seen before because we haven't had the combination of sensitivity, resolution, and field of view that were necessary to find these things.
Yeah, so I love the names of all of the ASCAP surveys. So, with this big telescope, ASCAP in which continent am I on? Oh yeah, talking about Australia, in Western Australia. And a telescope has, you have to decide what you're going to do with it, what you're going to spend most of your time doing. And it spends most of its time doing large surveys, as does Meerkat. And the surveys have these cool names of Australian animals, and one of them is wallaby. And so you're involved in wallaby, right? So tell us more about wallaby and what it looks like. So you've said that the ASCAP telescope can see a really big patch of sky at the same time. It has a large field of view. And so wallaby is looking at basically the entire southern hemisphere sky. And what is it looking for?
So it's looking for that, we talked earlier about the neutral hydrogen content of galaxies, and that's what it's trying to find. And at least in the, what we would say, the local universe. So it's worth putting a few things in perspective. As it goes across the whole sky, we expect Wallaby to see somewhere between 200 to 400,000 galaxies in H1, which, if you're used to hearing about optical surveys where you talk about millions and billions of galaxies, which is true, a few 100,000 is not a huge number. But when we talk about things that are observed and resolved in H1, there's like maybe 10,000 odd things that have been really resolved before.
Is that all? I didn't know that.
Like, there's not a lot, and so we're talking about an order of magnitude increase. And now I'm talking...
That's cool.
And going through all of those detections, now a lot of them are still going to be dots on the sky, but some of them will be resolved. And in radio astronomy, resolved has a very different meaning. So, again, if you picture a galaxy in your head, and you have that beautiful picture of a spiral, now reduce it to the size of 2 pixels. And so...
Maybe even 1.
Yeah, maybe even 1. So I'm going and saying, well, if we have 3 or 4 pixels, or the equivalent of a pixel in radio, which we call a beam for reasons. If we have 3 or 4 of them, we could give you a model of it.
Really?
Yes. And it turns out we can go down that small because radio has an extra property that optical stuff doesn't, which is that we automatically get the velocity of all the gas at the same time as we get the spatial information.
Ah, okay. So here we have it. Okay, so Wallaby is looking at hydrogen gas in galaxies in the whole southern hemisphere, and it's going to be able to resolve a lot of these galaxies, meaning that instead of just being tiny dots, that we can see their shape. We can see some of their structure. Now, some will be able to see a lot of their structure, and some will be able to see like 4 pixels worth of structure. But then not only do we have like a map of the sky, we've actually got a cube. We call it a data cube, where the X and Y axis is like what we see on the sky, like longitude and latitude on the sky kind of thing. And then the third axis is actually, well, it's what we call the spectral axis. So it's frequency, but it can also be considered to be velocity, right?
Yep, the sort of velocity of the gas as it moves towards or away from us, which, again, this gets very confusing to think about, especially as we're talking about it in an audio format.
Yeah.
But as I started working with this more and more, my picture of a galaxy, at least in radio, has changed sort of. So instead of thinking of a galaxy as this beautiful spiral, I think of it in the data cube where it's like a cigar. A long cylinder rod type shaped at a bit of an angle when you look at it in a 3-dimensional view, which is very different
Yes.
looking than the sort of picture that we have of beautiful spiral armaments, just because, again, as the gas rotates, some of the part that's rotating towards us is going to have a slightly more velocity towards us, and stuff that's moving away will have a slightly different velocity as well. And so that moves that gas into the back or the front of the cube, which then when you look at that in 3D turns into a cigar.
Okay, so like the galaxy is kind of elongated in that third dimension, and then you can see that. Now, I'm glad you mentioned that because, yes, this is an audio podcast, but we are going to put a little animation and a kind of movie on the blog. So I encourage you to go and have a look so that you can actually see what we're talking about. Because our other guests on this episode are 1 or 2 guests, I don't know yet, but we're going to be going into the Viz lab, the visualization lab, and looking at one of these galaxies in the hydrogen in 3 dimensions. And it's not easy to do, right? Because to look at something in 3 dimensions. And so we are now using VR, virtual reality goggles, and being able to look at this stuff, right?
Yeah, which is really exciting. It turns out that there is science that can only be done by going into VR. I think that's where this episode's going to go, so spoiler alerts ahead. But that's one of the things with Wallaby, and this is actually a true thing of every large survey that is untargeted, is that the most of the stuff that you're going to see is going to be small because it turns out the more sensitive you are, if you see more of the sky, you're going to pick up more little things that are faint, and you're going to run into noise. So there's all sorts of noise in the system, and a lot of the galaxies that we find in Wallaby, when you start looking at the noise, you're like, oh no, there's really a thing here, really. And it's only once you look at it in 3D that you can actually convince yourself, okay, no, there is something really here.
Yeah. It's not just interference from, I don't know, radio stations and mobile phones and satellites and things like that.
Yeah. It turns out this whole 3D structure is really important and really key for radio astronomy and for understanding galaxy gas.
Yes.
You can't deal with gas until you look at it in 3D, which is a weird statement to say.
It is a weird statement, but it's also true. Okay, so we have this method now of looking at radio telescope data in 3 dimensions with virtual reality, and we're looking at the raw fuel for star formation, or like the petrol of a galaxy. Actually, I like that. I don't know how we haven't used that before, but that's a good one, Nathan.
Yep.
I like that.
Yeah.
Okay, and we're trying to figure out, like how they stop at petrol stations and how they get their extra gas. Now, with the Wallaby survey and with all of this VR stuff, have you found anything interesting yet?
Yes, so in Wallaby, just to put in some context, Wallaby is an ongoing survey, and we've just finished looking at the first set of fields. And as we were looking through the first set of fields, we found a couple weird-looking things. One of them was really obvious right away, that there was a ring of gas that was moving differently than the main body of the galaxy. And you could just see that in the 2D picture of the galaxy. You could just see there is a ring of gas here.
So you can see like a galaxy and then around it a sort of ring of hydrogen gas. Okay, that's weird.
The other one we saw, you would never guess it from the picture of it.
Okay.
But when we looked at how the gas was moving, you could very clearly see that there is gas that, because of the orientation of the thing, it looks right on top of each other. It's a nice little circle on the sky, but it's a few beams across.
Mm-hmm.
So a few pixels across. So, we can see details. But when we looked at how the gas is moving, it looked really strange. And immediately we saw that there is, again, a ring of gas that is moving differently than the main body of the galaxy. So you had a cigar with that was going through a donut.
You had a cigar through a donut. I like that. That's a really good description.
But again, you would never see it in the image because the cigar and donut just look like one thing. It's only when you look at it in 3D that you see cigar through donut. The other one, again, you have a cigar, but then the ring is very clear. It's angled in 3D in that velocity space, but it's still the same thing. And so we spent some time looking at this going, this is weird. But then recalled that there is a type of galaxy that people have seen for something like 50 years called a polar ring galaxy.
A polar ring galaxy, okay.
Yes. So there are beautiful pictures of these in optical, which is that you have a galaxy. In optical, it's a particular type of spiral galaxy, but we don't need to go into that. There's a galaxy, but then there's a whole bunch of stuff orbiting it at 90 degrees to the main body of the galaxy. And so that's why we call it polar, is that it's going perpendicularly to the main body of the galaxy.
Okay, so you've got if you imagine a flat spiral disc and then 90 degrees to that, so perpendicular to that, you've got a ring around that.
Yeah. So think of a frisbee with a hula hoop running perpendicular to it. They're closer in size than that, but I'm going to use that analogy because that's what I picture in my head, of frisbee through a hula hoop. And so we've seen these in optical, and people have done follow-up and found some of them have gas, some don't. And people have seen that there are polar rings in gas that are perpendicular to the main body of the galaxy. What people hadn't really seen are gas where there's two distinct components, gas belonging to the main body and gas belonging to a ring. And so this was what we had found, but there is another difficulty when you find these, which is that
Okay.
we do have a three-dimensional view, but as we said, it's position on the sky and velocity. And so
Oh, it's not distance.
when you're thinking about a polar ring, you're talking about it in sort of XYZ coordinates, position coordinates, not velocity coordinates. And so you could imagine, well, what if that ring's not at 90 degrees? What if it's rotated in some way from 90 and it's only inclined, or what we would say is a warp from a galaxy disk?
Well, this is warping my brain now. Okay, so we've got this data cube, and the x and the y are position, but then the z-axis is not position, it's actually velocity, right?
Yes.
So this is confusing us. Okay, so we've got velocity information in the third dimension. We don't have position or distance, and so we kind of don't really have that much information about the inclination of the polar ring. Is that what you're saying?
Yeah, at least right away. And so the tricky bit about polar rings is that if you have a polar ring galaxy and you start rotating it in different ways, that ring is going to appear on the sky completely differently, even though it's the exact same thing. It's, again, the perspective. If you look at the car from the front versus a car from the side, they don't look like the same thing. And it turns out that it's really easy to hide polar rings in a picture. It's harder to hide it in a data cube because the gas is going to move differently. And so we actually spent a whole lot of time trying to convince ourselves of going, well, we see these weird cigar donut shapes. Is that a polar ring? And so we went and made a whole bunch of different models of, okay, what if I had a polar ring that looks like this, does that make a data cube that looks like this observation? What if I move my ring around? What if I change my galaxy's inclination? Can I get something that actually works? And we did. That was the exciting part. Or one of the many exciting parts is that we went and said we were able to find a number of polar ring models that fit the data, that look right.
Okay, cool. So here we get to modeling. So remember all the way back at the beginning, I said there are two ways to study the hydrogen gas and the what we call the kinematics, which is a big word, just meaning motions,
Yep.
the velocities, the motions of the gas within a galaxy. One is with telescopes, and we've just talked all about that and looking at the hydrogen gas in 3 dimensions. And then the other way is with models or kind of simulations of galaxies. And that is what you're working on, right?
Yeah, and so it's not simulations the same way as sort of building the giant cosmological sims of the universe, although you can do that. In this case, we go and say, what if my galaxy was really simple? What if instead of a super complicated galaxy, I pretend my galaxy is a frisbee with a whole bunch of rings in it? Each ring is exactly the same. And then we go
But they're tilted with respect to each other, right?
They can be.
I'm excited about this because I've just learnt about tilted rings modeling and I've taught my undergraduates this.
Yes, and this is in fact using tilted ring modeling. And so we go, what if it's really simple and it's a whole bunch of tilted rings? And then we can go and make this model of different rings and project them onto the sky and make mock observations. And if you have a mock observations, you compare it to the real thing and go, this looks completely different. This thing looks like a garbage truck. This thing looks like a rugby. But then you go, well, wait, this one looks like a cigar with the right shape. And now I can go add...
Going through a donut.
And now I'll go add another ring perpendicular to it. And now I've got my donuts right.
Okay, so you kind of like work backwards and reverse engineer it, right?
Yeah, so in this case, what we started off was try to get the cigar right, try to get the main body of the galaxy, and then we went and tackled the donut shapes or rings because that donut can turn into sort of a slice if you rotate it the right way. It's wonky looking. But yeah, so that's what we did was we tried a whole bunch of different polar rings once we had the main body sorted. And the only way we could do that is we had to start off with, go back to the observations and go into the visualization and break apart the donut from the cigar. We had to isolate the cigar from what we'd say the anomalous gas. And then we can
Anomalous
model
gas. What's that?
anomalous. So that we just say, that's gas that doesn't belong to the main body. It's an anomaly.
Okay. Okay. It's just weird stuff on the outside, outskirts.
Weird stuff on the outside that we start off and say, we don't understand it. And then we go and say, I have a guess. My guess was that it's a polar ring. So let me try a whole bunch of polar rings and see if any of them match the anomalous gas at the same time as matching the main body. And so once we had separated out the main body gas, we could make the main body model using tilted rings. Then we could focus on the anomalous gas and figure out, okay, if my ring is polar, then I only have a limited number of orientations. It's still a lot, but there is a limit on how that ring can be relative to the main body because it's still got to be at 90 degrees. And so once we make all those, then we can get our cube and match it up and go, yay, we got something that works. Hooray!
Okay, so you kind of start off with your observation, and that informs like the boundaries of your model that you can make. And then you make a whole bunch of different tilted ring models or whatever it might be, and you add in this polar ring. And then you kind of recreate mock observations, so what you would see with a telescope if this was the actual like structure of the galaxy and its polar ring, and then you see which one best matches the observation. Is that kind of close?
Yeah, I'm going to keep going back to cars because it's just easy enough to do. So if you go and picture a car, if your model is a dump truck and the observation does not look like a dump truck, looks like a Mini, then you know your model failed. If you're making a model of a car and it has two wheels, interesting model, not a car, sort of thing. And again, if our observation only has two wheels, then all our car things are going to fail and we need our motorcycle model, sort of thing. So that's sort of what you're doing.
Cool. And so you were able to create a model that was able to reproduce what we think is a polar ring galaxy for this one that was like a really weird like cigar going through a donut kind of thing. And then you've published a recent paper on it, right?
Yeah, well, so we found, these things are interesting. I think they're some of the coolest galaxies that you'll see. In optical, there's some of the most pretty pictures of galaxies that you'll ever see. But there's a number of interesting things about this. So we talked earlier about how do galaxies get their gas? How are they refueling? So an interesting thing about a polar ring is that a polar ring can't form when the main body forms. So that gas had to come in later on. So that gas has to be from a stop at a petrol station.
Oh, yeah. My next question was meant to be, like, how does the polar ring form?
Yeah, but the precise nature of how it forms is still a question. The most likely thing, again, if I'd put about 3 jelly beans on this bet, 3 to 4 jelly beans, is that it's from another if another galaxy comes by at just the right angle and just the right to the main body and just the right orbit, it can land in at 90 degrees and make a polar ring.
So like another galaxy comes close by and the gravitational pull of this galaxy like pulls some of the gas off into a ring. Is that what you are saying?
Yep, that's sort of what I'm saying. But another way is that there could be cosmic gas reservoirs that we
Cosmic gas reservoirs, okay.
Astronomers will talk about the cosmic web, where there's gas filaments through the cosmic web of cold gas that we still can't see. Maybe we can with the SKA, but right now we can't. Where the galaxies could be getting their gas from those sort of larger scale structures that we can't see. And again, if it's coming in at just the right angle, you can get a polar ring. If it's not 90 degrees, though, it'll just fall onto the main body of the galaxy without making a ring.
Ah, so it's like there's this filamentary web of cold hydrogen gas just out there in the universe between galaxies, and we think it's there, but we can't see it yet because it's too faint for us to see with our current telescopes.
Yep.
And we think that that's like basically constantly slightly refueling the gas in the galaxies, and in some circumstances, rarely, if it happens to fall in at the correct angle, it can form this polar ring. Is that right?
Yep. Like I said, there's these two different ideas that it's filaments or it's from mergers and interactions. And again, both of them to be at 90 degrees, you have to come in at just the right angle. Otherwise, you just fall right back down onto the main body. So polar ring galaxies, we're hoping to study them in more detail and try to figure out, where did that gas come from? Did it come from other galaxies? Did it come from this cosmic filament? If we can look at stars in rings, did those stars form now, sort of recently? Which would imply that the gas came in first, or are the stars old and they came in as gas and stars mixed together? So that's all stuff that we don't know yet, but astronomers always ask for this. We want better simulations and we want deeper observations, and please give us more telescopes.
Always, always. It's never enough.
You will never talk to an astronomer who will never, it's the end of every paper. It would be good if we had bigger simulations and deeper observations. Yes. Wouldn't that be great? We need more data to tell you for sure, but we've got an idea.
Yeah, but it's good because we're always working at the cutting edge, right?
Exactly. So that being said, there is another exciting thing about finding two of these polar ring galaxies. And that's that, one, we never expected to find one, but we found two. And so we go, okay, 2 is not a big number. But the optical people who've studied polar rings and stars have said, well, we think there's about 1 in 1,000 galaxies in the nearby universe have a polar ring.
Right.
So in the first match of Wallaby galaxies, we had about 200 that would be big enough on the sky for us to even see a polar ring.
Wow.
And so we found 2 out of 200. Again, maybe we got lucky, but 2 out of 200 is a lot more than 1 in 1,000.
So they might be more common than previously thought.
Yep, and there was an interesting paper on the archive yesterday, as of the time that we're recording this, of people looking in optical and went deeper in optical than they've gone before, and went and said, hey, we just found a whole bunch of new polar ring galaxy candidates.
Really?
And it was on the archive. Astronomers who talk about the archive is where we post our papers. But they said, we found about 1 to 3% of galaxies have polar rings in this deep optical. Hey, doesn't that match exactly what these radio astronomers just found of 1 to 3%?
Oh, cool.
So, again, it's not a guarantee that we're right, but that's a lot of supporting evidence that we were really excited to see. Of going, how about that?
That's really cool. Yeah, what timing. I hadn't seen that. That's really cool.
Yeah, it was just, like I said, literally yesterday it got posted. So, hot off the presses.
Awesome. Well, I mean, it's all very exciting stuff, and I know it's a work in progress as Wallaby continues its survey. It will hopefully find a lot more polar rings, and you'll be there to simulate them and to confirm them. And we look forward to hearing from you again when that maybe happens in the future. Until then, Nathan, where can our listeners find you, and do you have any final messages?
So where you can find me is, so I do have a website, which is nathandeg.com. That has not been updated in way too long. Technically, I have a Twitter account, but I don't actually use it to post things, or Instagram. Yeah, so you can find me, again, the website. Most things are just linked through my name. It is a unique enough name that there are not many other people out there. It makes searching for me really easy, which is maybe a good thing or maybe a bad thing, as the case may be. Like you said, we're hoping that we're going to find hundreds more of these, which would be very exciting. And even without finding those, Wallaby's doing some really cool science, and we're going to have the next data release is coming soon. I've been saying soon for the last year, which is not that long in astronomy terms. We're hoping early January-ish to have the next set of data released to the public. And I should say, all the data that we've talked about, you can go grab that yourself if you want to. It's going to be really hard to work with, but you can get it.
Awesome. Thank you so much for speaking with us, Nathan, and we hope to speak to you again soon.
Thank you so much for having me, and have a glorious day.
Bye.
Bye.
Wow, this was a really cool interview, Jacinta.
Oh, thanks. It was fun.
Yeah, and I think having a paper published from this work really shows the need for us to be talking about this today.
Yeah, definitely. I mean, it's cutting edge kind of stuff. I mean, sometimes it's a bit of a cliche to say that, but really, like, these telescopes are so much more powerful than anything we've ever had before. And so when we look at the sky with them, we're just finding things that we just didn't expect to see. And so this research is showing, like, here's some weird objects that we didn't expect to find. Let's try and understand as much as we can about them and predict whether or not we expect to see more. And then actually the predictions were right. And very, very recently, I think it was the day that I chatted with Nathan.
Oh, nice.
Yeah, or the day before maybe, that his findings were actually confirmed by another team. So that's really cool.
That is so really cool. And I think something that came out from the interview was the question, where does a galaxy actually end?
Yeah, it's a good question. And I mean, it kind of doesn't in a way. It kind of just peters out a little bit. And then you also have to ask yourself, what is a galaxy? Like, what do we consider a galaxy to be? Is it the stars? Is it the gas? Is it the dark matter around it? So which part of that is the galaxy, if not all of it?
Yeah, I'd think all of it is the galaxy because, when you describe what a galaxy is, normally we say a group of stars, and
Right.
we speak about, obviously, the dark matter part of it. So for me, all of it would be a galaxy.
Yeah, I mean, we can argue, okay, it's everything that's gravitationally bound to it, right? And orbiting around it. But then you can get little satellite galaxies going around a big galaxy, and that's not gravitationally bound. So does that mean the satellites are part of the big galaxy? Or, it's kind of arbitrary. So everything in space is not as well defined as we like to think it is. Everything kind of flows into everything else. And Nathan was speaking about these cosmic filaments and the cosmic flows. So we actually think that different galaxies, if we think of it just as the stars, for example, they may actually be connected through this like filamentary like strings of hydrogen gas, basically. So then maybe there are no such things as galaxies. Maybe they're all just joined together. And then galaxies themselves, like the matter that we can see with our eyes, so light from stars and the gas and the dust, that's all contained within a halo, like a big bulge of dark matter, we think. Of course, we can't see it, so we don't really know where it ends. So all we can use is gravity to try and figure it out. And to the best of our knowledge, they just kind of don't end. One galaxy's dark matter halo kind of merges also into another one. So yeah, really actually like a simple question, where does a galaxy end? Actually very complicated.
I think from what we can get from this is we don't know yet.
Yep.
But we know of stuff that makes a galaxy as it stands to the definition today.
Yeah.
And I know Nathan, and I've met Nathan before, and he's so enthusiastic. So I think the next step would quite be more interesting actually to see what is the next step beyond the polar ring galaxies. But just before that, in our next episode, we actually talk about how these galaxies can actually be visualized, right?
Yeah, exactly. So Nathan mentioned a bit about it already, and we were going to put that part as part of this episode, but we decided we had enough content for an entire another episode, so we're going to split it up. But yeah, basically, you can only see the sky in 2D. Like if you look up at the night sky, you can see stars, but they just look like dots, right? And they all look like dots on the sky, and they all look kind of the same distance away. Like we can't get that depth, that sense of depth. And that's kind of the same as what we see with a telescope. We can't rotate the sky except for like into 2 dimensions. We can't go into the sky really to turn it around and see what's there. But there are clever ways that we can kind of do that with virtual reality now. And so, yeah, that's what we're going to be talking about, because it's one thing to have data, but then to visualize it, meaning to be able to see it or to experience it or to understand it. Yeah, we're kind of getting into that era of big data where we need to be a bit creative in how we're doing science.
Yeah, and I think one of the ways is actually seeing things in 3D and recognizing that they are now moving from just a 2-plane to a 3-plane. And, I like saying to anyone who has done pure mathematics somewhere out there, I think they introduced this already in high school, where we are used to having the X and the Y axis. Thank you for that. But think about introducing a third plane, which is the Z axis, right? Which goes along. And I think just having that idea of I have another axis can bring about 3D and how you see things in 3D. So you can even take this, and I'm speaking to students here, probably also in varsity at the moment. If you're trying to get ways to visualize 3D, is if you're trying to think about quadratic equation, for example, I don't know, like y equals to x squared, you know, it's normally on a 2-plane, all you see is just like that cube looking up. But if you add a dimension to it, which is the z, you could see that it goes all the way to the back. And I think that's one of the ways you can just try to get used to seeing things in 3D.
Yeah, things that you would usually see in 2D, right? Yeah, so yeah, exactly. It's cool, and we're getting the technology to do it more and more now, which is exciting.
I mean, one more job done for us.
Yeah, exactly. And as an astronomy education expert, this must be particularly exciting for you.
I mean, it's really cool to, and I don't want to get into what we talk about in the next episode, but it's really cool to have these technologies to actually get a sense of how massive and how big and how amazing these galaxies are. But not just galaxies. Our whole universe is rich with all of these things that continues to open up a world of exploration for us
So
as astronomy.
exciting.
It is.
Can you imagine what the SKA is going to find? Oh, the Square Kilometre Array, the world's biggest radio telescope ever. Oh, can't wait. Anyway, we're getting ahead of ourselves, so we're going to end today's episode here, and then we'll see you in part 2 of this in the next episode.
And that's it for today. Thanks very much for listening, and we hope you'll join us again for the next episode of the Cosmic Savannah.
You can visit our website, the Cosmic Savannah, where we'll have the transcripts, links, pictures, and other stuff related to today's episode.
You can follow us on X, Facebook, and Instagram at Cosmic Savannah, and that's Savannah spelled Savannah. You can also find us on YouTube, where audio-only episodes are uploaded with closed captions, which can be auto-translated into many different languages, including Afrikaans, isiXhosa, and isiZulu.
Special thanks today to Dr. Nathan Deg for speaking with us. Thanks to our podcast manager, Francois Camphor, our social media manager, Sumari Hatting, and our audio editor, Jacob Fine. Also to Mark Olnut for music production, Michal Werchek for photography, Carl Jones for astrophotography, Susie Karras for graphic design. Thanks to Emil Menkes for video creation, Moses Makungo, and Abigail Tamiran for transcription.
We gratefully acknowledge support from the South African National Research Foundation, the South African Agency for Science and Technology Advancement, the South African Astronomical Observatory, and the University of Cape Town Astronomy Department.
You can subscribe on Apple Podcasts, Spotify, or wherever you get your podcasts, and would really appreciate it if you could rate and review us and recommend us to a friend.
We'll speak to you next time on the Cosmic Savannah.